Willem will tell you what that means.
Okay. So in programming, we tend to treat data as something that is unrestricted, something that can be used in arbitrary ways. We can copy it, we can discard it, and nothing will happen statically. But at runtime, something may happen. So imagine we have a communication channel. So that will involve a certain protocol, and we had better respect that protocol. Or a hardware device which we're communicating with, that may have a shutdown procedure, or a file handle that needs to be closed, as another example. Also, there's private data. We want to ensure that private data doesn't leak out to public channels. So what we want is data as a resource. And we want to be able to control how those resources are used. So if you know me, you know that I'm a fan of types. So what we're doing in our work is being able to speak about these things at the type level. Now, this is our external motivation. The internal motivation is that there's been a flurry of work in the last sort of decade or so on co-effects, which are ways of capturing what the program, the context that the program depends on, and effects, how a program influences its environment. And those are sort of fine-grained way of doing this at the type level, and it's been quite theoretical so far. So we introduced Granule, which is a programming language that actually makes that available for, well, not real-world use quite yet, but for experimenting and trying out new research. So let's have a quick overview what this is based on. So at the bottom, sort of deep down, we're a linear functional language. We have where every variable must be used exactly once. So linear logic then adds a constructor, a modality called an exponential, sometimes called bang or of course, which lets you use the data infinitely many times. Arbitrarily, you can discard them. So that's sort of, again, you can have resources which must be used exactly once, and you get unrestricted data. Then bounded linear logic gave us something where we can give a bound, so we can be a bit more fine-grained. And we generalized this to, well, this is generalized to graded modalities, and which lets us reason in even more fine-grained ways about how data is used. And then we found that combining this with index types, so GADTs for lightweight dependent types, gives us a very nice way of expressing how we use the resource in certain programs. So we get constraints that are generated from the grades, the resource algebras, which I will talk about later. They cause these constraints to be generated from the bidirectional type checking, and we use an SMT solver to discharge those automatically. Works like a charm when it works. In the demo, now it will work. So here we have a Granule program. I hope you can all see this. Please shout out if I need to make this bigger. I might be able to make it just a notch bigger there. Okay, so we have the identity function, polymorphic over any type A, and that is linear, so our type checker down here says OK. So we bind an X on the left, and we return it on the right. That's linear. Now, what happens if we uncomment those two programs here? Now we have two linearity errors. So on line 7 here, where we have the constant function that just takes an X, discards that, and returns unit, the type checker says linear variable X is never used. On line 10, we have an error, linear variable X is used more than once. So like linear logic, we can add a modality which says you can use this arbitrarily. So what I did this at the type level, but this also means that I have to do a value level unboxing pattern match, which gives us the capability to access that X inside of the box at an arbitrary type, at an arbitrary usage. Arbitrary type, that would be very scary. So that error went away, and we can equally do the same in this program here, in duplicate, and again, we do the value level unboxing. Now this is okay, but I don't think this is okay, because look, those two inputs, they're being used in a nonlinear way, but differently, and they look the same. So here come graded modalities, or the grades of the modalities. So here I can say I'm using the x 0 times in the first case, and I'm using it twice in the second case. So this is actually, these are exact usages. So if I say 3 here, then I get an error because 2 is not approximable by 3. Yay. But, I mean, those are actually quite boring programs because here we know statically what's happening, what the usage is. So let's look at introducing some form of control flow. So here we have data maybe the maybe data type, which we know and love. It's sort of a mix of Haskell and OCaml, yay. So here we have a function that, given a default value and a maybe a, will return an a. So I say to you, what I want to do here is I want to unwrap the maybe, and in the case of none, I will return an x. Now that type, doesn't really say that in a normal language. We might be in a nonlinear language. We might be just returning the default parameter in both cases. But let's see what the whole context says here. So here we're going to fill in xd. That's all we have in the context. That's OK. But now we're going to have a problem, because now we have both x and xd in here. So if we use x, then we get a linearity error. And obviously, if we use xd, we also get a linearity error. So here we're going to have to make the default value unrestricted as well. Now this is also not great, because here this is not super precise, because on line 19 in the sum case I'm not using it, so I'm using it 0 times, and here I'm using it once. So wouldn't it be nice if we could say something like this? Well, that would be nice, and in fact we can. Yay. Okay. So this is quite neat, because this implementation here is assuming totality is the only thing that satisfies that type. Yay to verification. Okay. So just a quick one now. So here is singleton encoded natural numbers, which give us reasoning at the type level about the value level, what the value level number represents. So if we were to define a function that, given some number n, applies some function a to a n times, then this is how we might start with the type signature. Now, in this context here, we have f and x, so if we return just x, as we might want to, then we get a linearity error. So we're going to have to make this parameter unrestricted. Okay, and now we can just fill in the recursive call. So we apply f to x once, and then we apply it m more times. And here I'm reboxing that f, which is called promotion, and that just means that's a check that all the free variables that f depends on, that the promotion depends on, come from a box themselves. So this should work now, if I didn't make any mistakes. That seems to be fine. But what happens if I actually do the wrong thing, which still satisfies that type? So now I'm applying the function n plus 1 times. So really what we want to be able to say here is the usage of this is n. Ooh, and that works. Cool. So now it says you've used it one more time. Okay, we need to translate that a bit, but basically it's saying you've used it f1 too many times. And now it's happy. So the cool thing is that all well-typed programs that satisfy, programs that satisfy that type and that are total are extensionally equivalent. Awesome. Okay. Right, so we've talked about graded modal types. Let's quickly dive into what that means. So stepping back a bit, modal types come from modal logic, and here we typically have two constructors, necessity, which is the box, and that's modeled by comonads, and we have diamond, also called possibility, and that's modeled by monads. So then if we change those to indexed families of modalities, where we have some additional parameter R, which is a resource algebra that captures the structure of a program, then we get more fine-grained reasoning about what the program is doing. So we saw examples of this just now. We had something like a box 2 means that we can use the a twice. We also, and I'm not going to be able to show this today because of time constraints, but this is also in the paper and you can try it in the implementation. We also have an effects system through, well, we can sort of model an effects system through graded possibility. So here we can say this A type is a computation that just writes. So we've had lots of slogans in this in the last few talks, and our slogan is this. So if you have a modal type system, and if you augment that with grades, then you can match the structure of the proof or program with the structure and the grades and get more sort of more fine-grained reasoning. Let's have a quick look at what types are in granules. So we have functions, we have modal types that are graded at some grade R, some base types which have elided, and R is taken from some resource algebra, which here I present as a semi-ring because that's what we're going to be needing, but that can be partial. So contexts here, they have linear assumptions, but we also have graded assumptions. And what that means, I think, becomes more clear if we look at an example. So here we have the dup function that takes an x, so that's what we've seen earlier, and that takes an A with a capability of 2, or a modal type A with a capability of 2, and it returns a pair. So this gets put into the context here after some derivation steps. We get a graded assumption with capability 2. Okay. Now, in rules where rules act on subterms, here we have T1 and T2, we have disjoint contexts, and then we're in the here we need to then join the contexts together, and that's a partial operation that could fail with a linearity error. And I'm going to give you one of the cases here, which actually shows how we can do contraction. So if x is used in both subterms at grade R and S respectively, then in the output context it's going to be used R plus S times, and this gives us contraction. And the unit of the addition it gives us weakening, so we can always add unused assumptions as long as they're graded at 0. So if we want to substitute some term t into a context where it's needed into a modal context, as we saw in the example of apply n, where we the recursive call where we use the higher order function, then we promote. To promote at capability R, we also need to scalarly we need to do a pointwise multiplication of the discharge context that T depends on. Sorry, I mean graded context. Okay. So then the unit of that, the 1, gives us dereliction, meaning we can turn. Thank you. That we can turn linear terms. Linear assumptions into graded assumptions at 1. Now I'm going to do one more quick demo of another different resource algebra, which is public sort of security levels. So here we have a patient record. So we have that record has 2 strings. One of them is public for the patient's city. One of them is private for the patient's name. We add lists. We've got a library of user-defined sort of data types and so on, but I've just added this to make things easier. So let's define a function that given a list of patients gives back their cities, because that's public information. We want to make that explicit in the type. So here everything is fine. Now if we try to return the name, so in this promotion here, we return the name, we get an error because we cannot move a private level value to the level public. So this is actually a very shortened example from the paper, but for sort of time reasons, that's the best we could do today. So what are our contributions? Well, we can mix and match as many graded modalities as you want in one program, and we have quite a few built in right now. So I just showed you about 3 today, but there's more to be seen in the paper. We developed novel notions of interaction between graded modalities via co-effect products. We also have interval grades, which we did see. Grade polymorphism is something we also saw. So in the apply n case. We also have resource algebra polymorphism, which again I wasn't able to show to you today, but we can actually be polymorphic over the type of co-effect we're using. And thus we can make sort of very generic analyses, which we can then instantiate at any particular co-effect. We developed the co-effects of pattern matching. And in general, our sort of implementation and our framework is meant to be a laboratory for experimenting with graded types and resourceful type systems. So we've managed to encode lots of nice things from the literature involving stateful protocols, and that's quite promising. The paper also contains formal definitions and meta-theoretic results. So some further work, very briefly. So user-defined resource algebras is something I often get asked about. So at the moment, because of the interaction with SMT, that's a bit fiddly to implement. It takes a few hours to add a new thing and a few more hours of debugging, probably. Full dependent types would obviously be nice to have further sort of fine-grained interactions. Ordered types, so going fully substructurally, getting rid of that structural rule as well, and maybe using modality to reason about that would give us more type-based verification. So further, we think that it seems that we can quite easily add other systems on top of Granule, like defuzz, contextual modal type theory. Something useful we can do something that would be useful given that our types sort of constrain the implementation quite a lot would be program synthesis. And Edwin Brady has some interesting results there, sort of empirical results with Idris too. Theory questions, we get, I gave you an intuition that this type is more constrained, so I think we get more theorems for Friese, and I'd like to develop sort of a more formal, rigorous model for that. We're also working on categorical models. So tomorrow, there's a tutorial, and we saw very little today. If you want to hack around and break some stuff, then please come along to our tutorial and install Granule. And don't forget our slogan, if you're doing modal stuff, then why not go graded? The end.
So let me again start with an anonymous question from Slido. So did your program examples use grades from program-level natural numbers?
Program-level natural numbers. Yes, so there's this connection between the value level natural numbers and the type level natural numbers, which we could then also use in the grade of the resource usage.
This was kind of a form of singleton types, right? So.
Oh yes. So should we have a quick look again at that definition? It was nothing special. It's literally, sort of isomorphic to vectors, indexed lists of specialized to unit. So, does that answer the question?
Yeah, I think so. So we had a question there.
Hi, thanks for the talk here.
Okay.
Can you elaborate on how you do recursion?
Okay. So this is something I meant to put on our future work slide. So at the moment, sort of in the presence of, we do have general recursion, and in the presence of general recursion, a lot of sort of guarantees break down, or we can't analyze things as much as we would like to yet. But I think we should have a conversation about that if you have any more thoughts. This is definitely something we're aware of.
Okay, thanks.
So Andre Bauer asks on Slido, so you noticed several times that your types have only one total and extensional solution. So what? So why is that a useful fact?
So I think it's quite interesting. So if we look at sometimes how we do verification nowadays, it involves sort of replicating the program definition inside of the data, sort of some data structures, and then the programs we write then have to satisfy that definition, but they're just going to be a copy of what So the specification and the implementation are kind of very similar. Whereas here, we've noticed that with certain programs, we can, if we reason about them in a resourceful way, then we get some sort of orthogonality between the types and what the implementation does. And the fact that we can then, potentially use that for program synthesis is quite nice, because I prefer writing types to writing programs.
So as a personal follow-up from myself, so
yes.
You mentioned three theorems in your future yes. work. So do I understand correctly? You want some form of parametricity that takes into account the grades of the types?
Yes, and also linearity itself. Yeah.
Okay, so no other questions from the audience. Let me check Slido. So can you explain a bit more how your treatment of context for graded modalities compares to Fitch-style presentation?
I'm not sure what is meant by Fitch-style in this context.
This is a question by Mark Hopkins. I forgot to mention, sorry.
So let me see, I had a slide on this, but it wasn't very... Okay, so we're using, if I understand the question correctly, we're using the method of graded assumptions due to Terui. And there's more in the paper. But I'm not sure if that was the question that was asked. So come and find me and we can discuss.
Okay, a question from Clara. Can I define a function f over grades and specify that I want to use a resource f of n times for...
So sort of some higher order...
Yeah, so I think some kind of type level computation with grades or something?
I haven't thought about that. I think we should try it out. I mean, there's some funky stuff we've managed to do, so come and find me if you have a particular example in mind, and we'll try it out.
Okay, so another question from... sorry. In the meantime, so you mentioned resource algebra polymorphism, which didn't seem to have any restrictions on algebras themselves. What's the use case for that?
Okay, let's have a... Yes, I'm looking for push and pull. Okay, so take something like push here, where we want, so let's just look at this one line here. So given a pair of A and B at capability C, we want to be able to push that capability down into the elements of the pair. So we can do that sort of thing. We have these sort of distributive or properties for any co-effect. So here we don't want to have to keep sort of monomorphically repeat this definition for all co-effects.
Okay, so maybe the final question. There was someone there.
Yeah. So you showed with the grades, you showed a way of specifying sort of a range of grades that is covered. Does this work only for like predefined, let's say for instance numerical grades, or does this also work for, let's say, the public and private that you defined as a user? Can you?
So it would work for any pre-order and or partial order, in fact, and we have and yes, the security levels are that would work for that.
So you can implement that entirely in granular. You can say, I define a new effect. This is my partial order, and now I want to use it as a...
No, so that's future work. As I said on the slides, that's future work still for us to be able to do user-defined ones. At the moment, you're going to have to hack a bit on the compiler to add it in. So just to give some background why we're not doing that yet. So there's interaction with SMT, and you need to sort of give the equations of your theory and for that to be fed into the SMT. And so right now that's the future work. But we accept PRs, and if you...
It's really easy. Okay, so let's thank all 4 speakers again.